the triangle inequality theorem. This says that the sum of any two sides of a triangle has to be greater, has to be greater than the third side. Otherwise, we wouldn't be able to make a triangle. Right? So, in the example they give up here is if you take 3 straws, one of 8 inches, 5 inches, and then 1 inch, try to make a triangle, that would be impossible because we would have some really long side, 5-inch side, and then a 1-inch side. There's no way for me to make a triangle out of those 3 sides. So there's 2 kind of things we can do with this. The first is this first set of exercises, okay, just to determine whether it's possible to form a triangle with the given side lengths. Now, technically, we would have to check that all 3, or that if we add these 2, it's greater than this one. If we add these 2, it's greater than this one. If we add these 2, it's greater than this one. But really, the only thing we need to check is if the 2 smaller ones, the sum of the 2 smaller ones, is greater than the third. Okay, so we really only have to check one inequality here. So I'm going to take the 2 small ones, add them together, and I want to see if that is greater than 6. Right, if that's greater than the third side. Well, 7 is greater than 6. That means, yes, 3, 4, and 6 could form a triangle. So like for number 3, if all 3 sides are equal? Yeah. So here, if all 3 sides are equal, that would be an equilateral triangle. So yes. And using this logic, right, we're saying, is 8 plus 8 greater than 8? Well, yes, obviously it is. So for both 1 and 3, yes, these can form a triangle. Prison? Yeah, so if we look at number 2, is that true? Is 6 plus 9, which is 15, greater than 15? No, it's not. Right? So this would be no. Now the visual there, okay, we're saying that we have some side length of 15, and then one side that's 6 and one side that's 9. If they're exactly equal, that would just form a straight line. Right? There's no way for me to move those sides up to form a triangle. Right? So if they're exactly equal, that cannot form a triangle. Right? Other questions? All right, so just take a minute or 2 here and try 4, 5, and 6. See if these 3 side lengths plus can form a triangle. So it's just saying you have a list of 3 numbers, right? Like A, B, and C, and they're in order from least to greatest. So what one inequality can you write that will determine whether the numbers can form a triangle? Inequality, like a greater than or less than thing. Okay.
So if they get bonus to do earlier,
What do you mean?
what's the first one? Well, the A.
Yeah, so we're saying if we add the 2 smaller sides together, it has to be greater than the largest side.
I was just picturing this in a water room.
Oh my god, I have a Jolly Rancher!
That was really exciting.
That's what it's happening.
Alright, so did we get Yes for number 4, no for 5, and yes for 6. Okay, so given 3 lengths, to determine whether those can form a triangle or not, we're just adding the 2 smaller ones together and seeing if that sum is greater than the largest side. Right? The other thing that we can do with this is given 2 lengths to find the possible ranges, or the possible range for the third side. Okay, so if I've got a length of 1 and a length of 6, right? So right, we're saying we've got sides that are like this. So we want to say, well, if I make that angle in between them really small, or if I make that angle in between them really big, what's the range that I can make that third side? Well, if I subtract these 2 numbers, so we're saying, like, here's my side of 6, and here's my side of 1. The smallest that I could make that third side, well, it would be like 5.0000000001, right? So we don't just want to think in terms of whole numbers. What we want to do is just say the difference between these 2 numbers, it has to be greater than that. So we're going to say that the smallest this third side can be is, it has to be greater than 5. Okay? Now, we're going to combine these 2 numbers into a compound inequality. So we're gonna write the 2 numbers first, and then we'll write the inequality here. So now, if we think about this the other way, okay, if I take my side of 6 and then I take my side of 1 and flip it all the way out here, well, now the longest that this third side could be would be anything less than 7, right? So like 6.9999999. So we say that that third side has to be greater than 5, but less than 7. So the way we write that is like this. Okay, x has to be greater than 5, but x has to be less than 7. Okay, this is how we write a compound inequality like that. The third side has to be less than the sum of those 2 sides. It has to be more than the difference of those 2 sides and less than the sum of those 2 sides. So to get the smallest that third side can possibly be, we just subtract those 2. To get the largest that third side could possibly be, we add them. So if we take a look at number 8, right, we've got sides of 12 and 18. Right, so we're saying if I put those 2 sides, kind of together, make that angle in between them really small, that third side, what's the smallest that third side could be? It would have to be at something greater than 6, right? 18 minus 12. Okay? What's the largest that third side could be? Anything less than 30. Right? We add those 2 sides together. So, what we're saying is we take sides of 18 and 12 and I kind of make the angle in between them really small. The distance between my fingers there, the smallest it could be is 6. But then if I make that angle really, really big, okay, almost to like a straight line, the distance for that third side, the largest it could be would be 30. Add 12 and 18 together. Subtract 18 and 12.
Up there on like number 2, how 6 plus 9, it can't be 15, but you just add them there and it can't be 30.
Okay, so let's say we make this 31. Is 12 plus 18 greater than 31? No. That's why it has to be less than 30. For these two have to add to be something that's greater than the third side. So it can't be anything bigger than their sum. It have to be less than their sum, third side.
And 6 plus 9, like number 2, is 15.
Right.
So why can't it be bigger? Can it be tiny?
If the sum of the two smaller sides is exactly equal to the third side, we would end up with a straight line. Right? If I say that this length is 6 and this length is 9, there's no possible way for me to raise those sides up. They would still connect. Right? I would just end up with a straight line if the sum of the two smaller sides is equal to the third side. Yeah, if I raise them up, they just wouldn't connect. Yeah.
12 and 18 make 30, so how could then it be 30?
It can't. We're saying it has to be less than 30.
Oh.
So it could be like 29.999, but it can't be 30. It has to be less than 30. And then same logic here. It can't be 6. It has to be something greater than 6. So it could be 6.001, but it can't be 6. Right? Questions? Okay, so go ahead and try 9 and 10 here.
I literally did that with the side.
It's the same addition.
I love the show. Very definitely great windows. I already did outside all day. I was coughing so bad, choking further. Stuck my head in the freezer. It wasn't over. I had asthma. I really closed my throat. I found out I had a cold. Wow. She didn't tell my brother this. Yeah, I had a glory. I don't know, but I sound like that.
Sorry.
Yeah, all this stuff.
Alright, did we get for number 9, x has to be between 4 and 7? And for number 10, between 74 and 90? Any questions on this idea here? Alright, so the last one on the front here, we kind of already talked about. Okay, so suppose you have 3 different positive numbers arranged in order from least to greatest. So I mean, we can just call them A, B, and C, or X, Y, and Z, something like that. What single comparison or single inequality will let us see if the numbers can be lengths of a triangle? So we know that this is the smallest, next smallest, and the largest of the 3 sides. So how could I write a single inequality that would allow me to see if these are the lengths of a triangle?
I never remember what they call it, so I just go that thing.
A plus B and that thingy, C. Number 11. So, yes, like we already talked about this when we did that first section there. If we have our three possible lengths already arranged from smallest to largest. We just have to take the two smallest ones and see if their sum is greater than the largest one. Yes. Okay. So, any questions at all on the front? We're going to do the best.
7 and 8. That's the only one that only one.
These are huge.
I have no idea what's split there.
I'm bringing them back.
If we have to make that size, the statement size.
Yeah, I don't think
So, proofs like this are, we're not going to write entire proofs like this, right? If we see proofs like this, it's going to be like the example on the bottom where there's a few missing pieces, right? So, let's kind of go through one of these together here. They give us that these two triangles are congruent in this example. And they want us to prove that this side, so AB plus DE, is greater than AD minus BE. So the sum of these two sides is greater than the difference of these two lengths here. Okay, well, we know that the triangles are congruent. And then we can also use the triangle inequality theorem here to say that these sums, so like AB plus BC, has to be greater than the third side, and then same thing here. DE plus EC has to be greater than the third side. Right? Well, I can use subtraction then, okay? For an inequality, we can subtract things and add things to both sides. So what they did was just subtract BC over to this side, and then subtract EC over to this side. Then they, let's see, what did we do here? For step 4, we added DE to, so we're looking at this inequality here, and we added DE to the left side, and then we added this CD minus EC to this side. We can do that because I know that DE is greater than that difference, so this inequality would still hold. And if I add something that's greater to the left side, and something that's less to the right side. So then for step 5, they just kind of rearrange things. Just move the CD over here, minus BC over here. For step 6 then, we grouped the BC and the EC together and pulled out a subtraction sign. So that's almost like reverse distribution. Right? Grouping the BC and the EC and pulling out a subtraction sign. Then they actually used the segment addition postulate to say that we know AC plus CD equals AD, and BC plus CD equals BE. Where are you at? Well, we're trying to show that we add these two sides together, that sum is going to be greater than AD minus BE.
No.
No. We're subtracting things, not adding. But yeah.
Like BE minus BA.
Well, they're technically the other way around. AD minus BE, but it'll be the same difference.
And then
That's okay.
We're trying to prove that AB plus DE is greater than the difference of AD and BE.
oh, I see.
So then, Finally, once we use the segment addition postulate, they're just substituting over here. They're saying that AC plus CD is just equal to saying BC plus EC is just equal to BE. Okay, so this was kind of a long way to prove that the sum of these two sides.
What way would you, like, you don't have to go through all of it, like, what would you show?
I probably actually would have just gone with, we know that AC and CD are congruent and BC and CE are congruent. So if we subtract all of that, I would have shown it in a nice way that if we subtract those two, we would get 0. Then the sum of two non-zero sides would have to be greater than the difference of two sides that get a 0.
So you would calculate
Probably, yeah.
Is there a possibility
Yes, there is. That's just the. Oh my gosh, what is the name of that? It's an algebra thing.
I was gonna say you could just say that equals if those two equal each other, and then if minus something equals 0, just x greater than 0, and then substitute 0.
Yeah, we could definitely do it that way. Yeah.
that makes more sense. Like, if they're both the same.
Right. I mean, this, for using the triangle inequality theorem, this probably isn't the best example because it was 0. So this is just kind of a forced way to show the triangle inequality theorem in proof.
I don't know.
What?
So the homework is going to be out of the book. I mean, I want you to practice the stuff we did on the front, too. Good?
Just skip it.
So